Okay,
All
well,
right.
I mean, I can.
I guess we're gonna start from the top here. So,
There we go. Nice, maximized. Oh, okay.
all right, can you read the text on the right here, or is it too small?
If I hold my laptop close to my face, a phantom type is a parameterized type whose parameters. Yes.
Let's do
Yes.
this. That's probably
Okay.
better. How about the code on the left? Is the code readable?
Yep. I can. Yeah, I can see it.
All right, cool. I'll bump it up like. Oh, actually, it was already bumped up a bit. Yeah. Okay. So, yeah, a phantom type is a parameterized type whose parameters do not appear on the right-hand side of its definition. And here they give us an example of something called const. This is basically a const functor if you're familiar with category theory.
I'm not.
Okay. Uh,
Yeah. Just to be clear, like
I,
I am
let
have
me
very little
let me
like
pull up.
formal knowledge of functional programming. Just so you can sort of like pitch the explanations at an appropriate level, if you don't mind.
Yeah. So basically, what this thing on the right here is doing is defining like a new, I guess, case class sort of thing, or like struct with like two fields. So something maybe like this,
Okay.
and it'll have a single field called a. So this will have a bit. The getter for this thing would just be the letter A. I can even like create one if you want. So we'll have
Okay.
like a const equals. Actually, we could do this. We don't need the new keyword in Scala. But essentially, I could just instantiate as like int bool, and as we can see, we don't use b. We only use a. So we're gonna just give it an integer of like 3, and then if I wanted to actually get what's inside of that, I can just call const.a, and this is just a getter. So that's
Okay.
the gist of what's happening here. This double colon, you'll see this a lot. This is basically a type ascription. It says that this thing on the left has this type, and you'll notice Haskell has this kind of syntax where everything is like lowercase for the type parameters, whereas in most other languages that we're familiar with, everybody likes the uppercase letters. So that's another difference that you kind of just have to get used to. But yeah, this is basically the same thing as what I have defined right here. So here they're saying that const is a phantom type because the b parameter basically isn't used. It doesn't appear after the equal sign, and you can see here like I have this parameter b, but it's not being used. That's literally all there is to this. That's what makes this a phantom type.
Okay. So why would we ever have a phantom type if we don't use B? Why wouldn't we just not include it in the definition?
That's what we're going to learn about. So it says
Okay.
that phantom types are useful in a variety of contexts. In data.fix, they're used with type classes to encode precision being used, and with smart constructors, they even have like an actual wiki page for smart constructors. I did talk about this before, in like on like my blog, but yeah, they actually
Okay.
have a page for this here. Or GADT. This means generalized algebraic data type. We don't really need to know about this. These are a little bit more complicated. They're
Okay.
worth their own video, I think, probably, if I were to do one. Encode information about how and where a value can be used. It can help to avoid kind signatures, or with more exotic extensions, they can be used for encoding bounds checks in the type system. Okay, that's kind of interesting. Since values of type
Okay.
parameters.
Could you give me like a concrete, simple hello world type example of where a phantom type would be useful? Because I'm still
That's what's
struggling.
going on down here. That's why it says simple examples.
Ah,
I just want to read the
okay.
rest of this first. Since the values
Okay.
of type parameters in a phantom type may be unused, they are often used in combination with empty types. Okay, let's look at what an empty type is. Empty type is one that has no values. They're often used with phantom types or type with. Okay, so empty type is basically like if you think of types as sets, it's an empty set. So like void in Haskell. I think it's called never in TypeScript. I don't know if there's. I'm pretty sure this doesn't actually exist at all in Rust. It's called nothing in Scala, so yeah, that's not really a big deal. Phantom types are nearly always either new type or data. Okay. So let's create phantom type synonyms, but they're essentially useless since synonyms are expanded at compile time. The phantom type variable will be discarded. Okay. Interesting. I think type synonym in this case is talking about like a type alias. Like in Scala, I could say something like type my const a equals const a, and then I can actually I can kind of like partially apply this thing and give it a value here, or not a value, a type. So now instead of having to constantly pass in like int everywhere, I can just use my const and it'll always have an int for the second argument. I think that's what's going on here with this phantom type synonym thing. So anyway, let's start looking at simple examples.
Cool.
So a phantom type will have a declaration that looks something like this. Okay, so I'm going to start trying to translate this stuff into Rust, because that's what I'm primarily about. I have Scala Fiddle here open because I think it's easier to explain certain things with Scala, but yeah, I'm going to try and aim to recreate this stuff in Rust. So I did prepare a little bit beforehand. I am aware of one limitation of Rust. The limitation of... Actually, let me just demonstrate it. So if I have a struct like the form data one that they showed here, and it takes a type parameter a, and let's say that it just has a single field. So this is basically saying define this thing as a struct with a single field string. So we're going to call this I don't know, data. Give it type string. If I try to compile this, what's going to happen is it's going to complain, or at least it should. Yeah, it says parameter a is never used. You have an unused type parameter.
Right, yeah. If you're just going to put a string in there, what do you need a for?
Exactly. So it says help. Consider removing a or using a marker such as standard marker phantom data. And so that's pretty much exactly what I have to do. I even have like the page open here. Here's a phantom data. It's a zero size type used to mark things that act like they own a t. So basically, what's nice about this phantom data thing, standard marker phantom data. Yeah, what's nice about phantom data is that it actually is it's cost free. I can define a phantom here and put phantom data there, and at compile time this thing will just disappear, so it doesn't actually take up any data in our struct. It doesn't use up any bits or bytes, so that's kind of nice.
So, sorry, just the compiler is intelligent enough to know that you never use that, so it just eliminates it entirely?
Yeah, I think phantom data itself is something special that they defined that it essentially is used purely at compile time as sort of like for like type checking, but the compiler knows that this thing doesn't actually exist, so it can just erase this and then.
So then it's a way to get rid of like compiler errors that you want to get around. If for some reason you have some type error that you need to get rid of, and you know for sure that it's not going to be any.
This is more like, I guess this allows you to actually have like type errors at all at compile time. It's just that after, like, well, once you compile the code, the I guess resulting bytecode or assembly or whatever is not going to, like, this isn't going to actually take up any space in this struct. This is essentially what this is.
So it's not going to take up any space because the compiler will just ignore it and construct the struct.
Yeah, it'll construct the struct as if this didn't exist, because it knows that this isn't actual data. This is just for marking that there's a type here, or a type parameter.
Oh, okay. So sorry, how is that phantom data tied to that type parameter? I'm not really familiar with Rust syntax.
How is it tied? I think that might be related to this compiler error that I'm getting. So it says accepted one of exclamation mark or double colon, pound semicolon. Oh, I forgot to use. That's why. That's my mistake. And it says the phantom data expected at least one type argument. That's
it's
how it
going
knows.
to take the A, right?
Yeah. So we're going to actually
Okay.
give it.
Okay, so what's going on here? So we're saying, compiler, stop yelling at me, telling me that I didn't use A. Here, take this phantom data that doesn't actually exist, that's going to use that type, so you stop yelling at me?
Yep, that's pretty much all it's doing.
Okay.
Yeah, so this is...
Okay.
Obviously, this is not as nice as this, where you can just put B here and not actually, do stuff with it. We don't have to have it here for the compiler to say, that's okay. But, there's different encodings, different limitations.
I think I can see what's going on here in terms of, okay, we need to use A in order for us not to get a compiler. What I don't get, though, still is, you could also just not make form data generic, and then you don't have the issue because you're not using A anyway, so why do you need to make it generic?
It's a good question. That's why we're going to continue looking at this example.
All right.
So this looks strange since at first it seems the type parameter is unused and it just could be anything without affecting the value inside. And indeed,
It does.
one can write this function. So this is basically saying we have like a label change type with this type. It takes a form data of type A and it returns a form data of type B. We can just do that in Rust as well. So I'm gonna write this as a function. Change type takes a form data. Let's do this. A form data type A and returns a form data B. I need to declare my type parameters. And essentially what this is saying is it's going to be taking a single argument here. This is actually just, I think this is just doing like a pattern match. Yeah, so this is taking a form data with a string inside of it, and then this, essentially it's assigning a string variable. It's sort of doing a destructure. Maybe I can show this in Scala. That might actually be a little bit easier. But essentially, you can actually destructure on case classes. So if I create form data here, I was not expecting to actually to do this in two languages, but here we are. Oh, actually, we don't have a field of that type. I'm just going to call this that, give it a string, and we're going to define a function called change type, which takes a form data. Okay, we got to declare our variables again. So, form data. Form data B. Alright. Essentially, we can just do something kind of cool like this, where we take a form data with some variable string, we call it str, and return a new form data. Are you following?
The syntax is a little bit unfamiliar for me here. So what your
okay, so
this function takes a form data that's what is the square brackets syntax?
Square brackets is the same thing as these triangular brackets.
Oh, I see. So it's okay. So it's assigning a type to form data. So we're saying this function takes a form data that's been typed as A and returns a form data that's been typed as B.
Yeah.
And we but it's basically like a switch statement inside.
Yep, exactly. So this is like a switch statement. It has a single case in it which matches a form data, and we know that this is a form data. And it takes and extracts the string out of that form data.
So that would be if, yeah. So if A is a string, then do this.
Yeah, and then it'll store string in like an intermediate variable, in like a local variable.
Okay, so can we actually see this thing get invoked? Can you invoke this guy?
Okay. Yeah, we could certainly try. I'm gonna get rid of this stuff up here because it might cause compiler errors. It probably won't, but like, I just don't want it to get in the way. So let's create a new form data. Let's give it a type int.
Okay.
You're gonna give it a string. How about hello? Let's see if that's okay first. Yep, it's fine. And now we're gonna try calling change type on it. So I think I have to actually declare the type up front here, because these are type parameters, right? So I'm gonna give it int, and we're gonna give this a second one bool. We're gonna give it the form, and what that should do is it should just give us another. Oh, oops! It's not called bool. It's called boolean in Scala. It's called bool in Rust with the lowercase b. But yeah, there you go. That's change type.
Okay, so that doesn't actually trigger the switch, right? Because it's an int, it's not a string. So what does this actually? This returns nothing then?
No, it returns a form data with hello. In fact, what I could do is I could even do something like this. So now what it should do is it should return hello world. Do you see what's going on?
So sorry. So str is referring to a type or a member variable of form data?
Str is a member variable. No,
Oh,
well, maybe not a member variable. Okay, so what it's doing is it matches this structure. This is pattern matching, by the way. It matches this structure against what it sees here. So if I had two fields, then I'd have to, like if I had, I don't know, foo, which is a type boolean, then what I could do is I could match this here and I could get a boolean out. And now I have a boolean variable to play with in this context here. Not that I would actually really want to do anything with it, but
okay,
I could match on that.
Okay, so this is kind of unfamiliar for me. So usually a switch, you're like matching on the value of a particular member variable or something here, but it seems like we're doing a switch sort of on the structure of the...
Yeah, that's exactly what we're doing here.
Okay, so this will always be triggered then because of the way you've defined form data.
Yep,
right?
Exactly.
Okay.
Yeah, there's only one case.
Gotcha.
So this is pretty much exhaustive because of form data being, well, there's only one form data, right? It can't be anything else. It's not really
Gotcha. Okay, so we're doing a switch on the structure of form data.
Yeah, and another thing that I could do is if I wanted to make this non-exhaustive, then I could add like true, and now it'll only catch the case where the second argument here is true. And
so you can put some references to the actual values as well.
Yeah, and then I could do something else here if I didn't catch this true.
Right.
So if it was false, basically, then I'd have to do something else.
Right.
That's the basic syntax of what's going on over here on the right. So they're doing a single pattern match. They're trying to catch all form datas with a string field, and then they're going to create a new form data with that string, the same string. It's basically like the identity function. You can think of it that way. And as you can see, yeah, all we get back is well, if I just remove all this extra stuff I added, you'll see that it just gives us back the form data with hello. So it's nothing special right now. All it did is it changed the type of the form data from a form data int to a form data bool, but of course the contents are exactly the same. Nothing has changed. And that's pretty much exactly what'll be going on here. I guess we can try and do the same thing in Rust and see what that looks like. So we have a form data A. We need to return a form data B. But and we know that the contents are the same. It doesn't really matter what we do, but Rust won't like this. So if I just do this, I'm pretty sure, yeah, Rust is going to complain about that. It says it expected a type parameter, found a different type parameter. So we kind of have to do the same thing that Scala is doing here. So we basically construct a new form data from the old one. So what would that look like here? It would look something like this. Oops, let's move that. So remember, this is Rust. It has a significant limitation here. We actually have to specify the phantom data up front. So we have a phantom data of type B now. And we'll say that the data field will just be form data dot data. And I'll put a comma here, in theory. It should all work. It should all compile. No, chain comparison operators require parentheses. Oh, what? That's interesting. Oh, maybe it's because I need to do this. I think that might work. No, so it doesn't like that. Why don't you like that? Is it because I need to turbofish this?
Turbofish?
Yeah, they have a... Yeah, I do need a turbofish. Okay, so turbofish is this cute little syntax. I don't know if I should call it cute, where you have this little double colon, and then you have this little shape here. So it looks basically like this, and these are supposed to be like the bubbles trailing behind the fish as the fish swims to the right.
Oh.
It's affectionately known as the turbofish syntax. It's used for things like if you have like an iterator, and you want to do like a map, and then you do like a, I don't know, fold, or, well, maybe not a fold, but like a filter, and then you want to collect it into like a vector, for example. You would have to be like, oh, if I want to specify the exact type, I have to give it a vector of, I don't know, int 32. So that's what turbofish notation is for. It's for specifying types when you're like calling a function. It's the same thing as basically if I was explicit here and I said this one is like Boolean now, this new one. Obviously I can't do that here. In this case it'd probably just be like B. I think that still works. Yeah. So turbofish is required in Rust, in Scala. This is the equivalent to it, and it's completely optional. You can just resolve that. So yeah, that's change type. Let's move on. So we can write this change type function to change from one type to any other. However, if the constructor is not exported, then users of the library that define form data can't define functions like the above. So the type parameter can only be set or changed by library functions. So we might do something like this. So here we have two structs. We have validated and unvalidated. So I'm going to define a couple of structs right here. Validated and unvalidated. Now, again, this is another function. So here we have a function that takes a single string argument and it creates a new form data with that string. Let's just go ahead and try and do that. So I guess this is just a constructor. There's a couple of ways you can do this in Rust. If you really want, you can do like impl form data. Oh, I need to declare my type parameter. I could do this and then give it sort of a object syntax where you can use like a, sort of a more object-oriented notation for this. And this also would allow you to better encapsulate your data, because then you can actually give it like modifiers like pub, and actually I think that's the only modifier that Rust has as far as I know. So you can mark stuff as like public. I'm not going to do that right now because this is simpler. We're just going to go with pure free functions. This what happens when you write code in too many different languages. You start taking your habits from other languages, and you're like, oh yeah, I just need to, you know, do this camel case thing. No. Are you still there?
Yep, still here.
Okay, cool. Just checking. So we're going to define a new function called form data. This is just a constructor that takes a string. In Rust, there's actually two types of strings. There's this one, and then there's this guy. This is a string reference. So this one is a stack allocated string, or like a reference to a stack allocated string, because, you know, strings are actually just arrays of characters. Here we have a heap allocated string. So it's like a boxed string. You can kind of think of it that way. And
what is a boxed? What does that mean again?
Box is basically a heap pointer, a fat pointer. You can just kind of like point to some data like this on the heap.
Okay.
So yeah, string is a heap pointer to a string, and so essentially we can take ownership of the string. It's a lot simpler, but it is a bit slower because you have the heap allocation going on. So you do have to be careful of that. But for the sake of this I guess talk, I'm going to just take ownership and use the heap allocated strings.
Okay.
So,
but because this is Rust, you don't have to worry about deallocating that string when you're finished, right?
Yeah, so as soon as it leaves the scope of this block of code, it'll be deallocated.
Automatically.
So if it was this, and I did return it here, or if I didn't return it there, if I did this, it would borrow the string from whatever scope called this. It would take a reference to that string, and then at the end of the scope, it would let go of that borrowed of that string. So
but it's just a reference. It is
just a reference. So
living somewhere else.
Yeah, it actually lives somewhere else. Like it could live in main. I could like go like let my string equal hi, and then I could pass it to form data like this.
I see. So we're passing a reference by value.
Or actually, right. I don't even need this because this is already a string reference. All string literals start that way. They're actually, I think they're usually they're usually something like static.
At the end of form data, the reference to str would go out of scope, but str itself would continue to live on.
So then, like, if I wanted to, so this is what they usually talk about when we're talking about like an affine type system. In an affine type system, you can only use a variable. I think it's 0 or 1 times. So if I owned this string, if it was just like this guy, and I did .to string here, what this would do is I'd pass it into this function here that takes a string, it deallocate it at the end of the scope, and then if I tried to refer to my string again, it would say, uh-oh, compiler error, because I used this variable more than once. So essentially, we say that Rust has like an affine type system. I mean, it's not maybe exactly like that because you could just use a reference here and then you could reuse this variable again later, but yeah.
Yeah, it's interesting. I'm trying to align that with what I know about C++, where you pass things by value or by reference. Seems like kind of a twist on what goes on there, but you still have to be aware of sort of similar issues.
Yeah, it's very similar. C++ does have like you can like move data. There are move semantics, so it is kind of like an affine type system there. The only difference is that it's C++, so there's a lot fewer safety rails. It'll let you do a lot more things that are definitely invalid within the context of an affine type system. But anyway, I don't want to talk about C++.
All right.
Anyway, we were writing this, I guess, constructor function. So it takes a string and gives us a form data unvalidated. And It's basically just going to do this, what we're doing in change type, except we're actually going to give it unvalidated as the explicit type argument. And here, instead of form data.data, we're just going to give it s, our string. Obviously, if this was like someone else's code base, they might not like things like single letter variables, but for the sake of a demonstration, I don't think that's a big deal. Yeah, we have a bunch of dead code here. That's fine. So this is our constructor.
So,
yep.
Sorry, just a Rust syntax question. So there's no return keyword? You're just returning
There
that
is no return keyword
form
whatsoever.
data.
And that's similar in Haskell. You'll notice that I didn't put return form data here.
Right. So what determines where you return from?
In Scala, it's the last statement in your code. So
sort of like an...
So if I had... Yeah, essentially, it's like if I had like a whole bunch of stuff here, I could do like a, I don't know, print line, yo, what's up? Wow, never mind. But essentially, I could do anything I wanted here, and then the last one is the one that gets returned. Rust is similar, but they actually they have a sort of annoying difference, actually. If I want to have multiple statements in a block of code, actually, this is not a good function to use. If I, how about this one? If I want to have multiple statements, I have to have a semicolon. This is not something that you have to do in Scala, right? They're actually like using white space here. In Haskell, it's the same kind of deal, sort of. Well, it's similar. They use like the let in syntax. If you want to do something kind of like this, you've seen that before. But essentially in Rust, what this does is it says that this is an expression that returns a type called unit. Unit is the same thing as void in C++ or Java. It's essentially a singleton set. It's like there's only one member of this set. It's this guy, this open and close parentheses, and it essentially is nothing. So any function that looks like it takes nothing, like main, is actually taking one of these guys. And if it doesn't return anything, so to speak, it's actually returning one of these guys. There are reasons for why this is and why we don't just use like the nothing type, because there is that nothing type, or I guess that void type, the empty type that I was talking about earlier. That's usually used to indicate that a computation, or you can't like create that value. So you can't call this with nothing because you can't give it a value of nothing. There are no values of nothing. So we use unit instead. And same thing for like if we're returning nothing. Like if you could return nothing, then you could construct a nothing. But since the nothing type is empty, there's no way to do that. Does that make sense?
Yeah, I mean,
it's sort of a semantics kind of thing, but
it's like, yeah. I mean, I obviously understand what void means, and I understand that there are some, extra steps that are necessary to make that concept work.
Yeah, it's more of like a theoretical thing. Like I think the actual code itself doesn't actually create like a value for that. It doesn't actually take any memory or anything. But yeah, it's purely a theoretical concept.
Yeah. Well, I think at this point in my Rust journey, I can just sort of consider it boilerplate and not worry about it too much.
Yeah, pretty much.
So I understand other things, other more fundamental things.
It has more implications when you start thinking about like the Curry-Howard isomorphism, where you basically think of types as predicates in like first order logic, and you're thinking about like, oh, if I can construct a value of this, that's basically the same thing as saying like this is true, or if I can't construct a value of this type, then it's like false. So yeah, there's a reason for why it's kind of structured that way. But anyway, that's not really important. Yeah, essentially, if I'm going to have multiple statements, I have to have a bunch of expressions that return unit, and then the last one is an actual expression that returns a value. So if I put a semicolon here, that's bad, because now I'm saying that this returns unit, when the type here obviously is not unit, and this will actually result in a compiler error. Yeah, so this function's body doesn't return found expected, form data, found unit. So it's kind of annoying. That's just how Rust works, though. So yeah, that's this constructor. The next thing we're gonna do is implement this function called validate. So do nothing if the data doesn't validate. Okay, interesting. Oh, actually, no, nothing. Okay, so there's something really annoying about all these different languages. Is that so Scala is inspired by a language called OCaml, and in OCaml there's a type called option that essentially can be either a sum or a none. In Haskell, we have something called a maybe, and this can be either a just or a nothing. You can kind of see the
interesting. So
similarities.
this is like the lowercase b bool versus uppercase b bool.
Yeah, so this is like a more Haskell-y notation. In fact, I think if I just did that, that would actually be valid in Haskell. This one would require a bit more work. So Rust has the same thing as Scala does. It's called option, and it would essentially be something like this, where we'd have Rust enums are not like your typical enums. They're not like what you would see in C#, for example, or Java. Rust enums are actually more like discriminated unions, which you would see in like C++ or TypeScript. Essentially, we'd have like a sum, which takes an A here. Oh, actually, I don't remember the exact syntax for how this works. I'm drawing a blank. It would look something like this, though, and a none. And then, essentially, if you wanted to construct one of these, you would have to do something like, I don't know, option, sum, A, or whatever. But I think Rust does some has some like syntactic sugar for this, so you don't have to have this thing here. You can just say sum A. Let's go ahead and play with that right now. So essentially, that's what's happening here. This is a, I guess, optional type. It's sort of an effect that represents the nullability of form data validated here. I guess we want to start by taking a form data again, or I guess unvalidated form data.
I like the error messages generated by the compiler and how they sort of, rather than just giving you like a line and a column, they actually visually show you where the issue is.
The error messages in Rust are actually they're, for the most part, they're actually really good. That's one of the things that a lot of people praise Rust for, is its awesome error messages. I think they're pretty cool. So here we have option. It's a little bit verbose, unfortunately. Form data. This one has type validated. So now we're kind of bleeding.
Right, so either we're going to fail the validation and return none, or we're going to successfully validate and we'll return the validated object.
Yep, exactly. So how am I going to do this? So we have this unvalidated thing. I guess what we would do to validate is check something like, I don't know, if unvalidated dot... Actually, Rust is like Python. No parentheses around your if clause. Or at least the Boolean condition there. Oh, hang on. Yeah, this is right. We could say that it's invalid. So here they're talking about form, like sanitization, like sanitizing the input to make sure that no one injects like some kind of script. Here, I'm not going to do that because I don't want to. I'm just going to say that it's invalid if the length is greater than 8, for example. That's not how that works. How about that? I think that's a valid function on string. So here, if it's greater than 8, then we say it's invalid. We want to do nothing, so we're going to return none. Otherwise, we're going to return some, and it'll be just another. So remember, we have to actually give it a new type, validated. So we can't just do this. We need to actually explicitly go like validated. What am I doing? Form data. Validated. I don't know why I did this. This is silly. This is me not being able to input things good because I suck. So we give a phantom data, of course, and then we give our data itself. The data will be exactly the same, so we'll just take the unvalidated data and move it over to this struct. So this struct will have ownership of this, and then it won't be deallocated yet. If you'll notice, again, there's no return keywords, right? Like normally, you'd have to store this result in some kind of like intermediate variable, but Rust, like Scala, has if expressions. They're kind of like ternary expressions. So instead of doing this whole if blah 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 blah, in C# you might put like a question mark here, and then instead of this else you'd have like a colon, right?
Yeah.
In Rust we don't do that, so we just flat out return the entire if like this. But it's the exact same thing, just syntactic differences. I think this.
Well, it's sort of like you have. I mean, for me, coming from like a C# background, you have an invisible return in front of the none and an invisible return in front of the sum, right? So
yeah, you can think of it that way. I like to think of it as like this whole thing is what's being returned, just the entire.
Right. Yeah, I see what you mean. Yeah, and then that's I mean, sure. I think it's sort
really
of a tomato kind of.
Yeah,
situation.
it's kind of nice. It's kind of flexible in like how you can kind of reason about this.
Right.
But anyway,
Okay.
that's our validate function. And finally, we have a use data function. So this guy has a kind of interesting type signature here. It returns an IO of type unit. What this is saying is that this has the effect of performing IO. And remember, Haskell is a purely functional programming language. So I can't just execute like a print or anything. I can't actually just execute things.
Right. It has to be.
I have to like store it into like a data structure, and then
Right. So
it kind of describe the program, and then eventually it would get interpreted and then executed. So Rust, as you may know, is not it is strictly evaluated for one thing. It's not lazily evaluated like Haskell is, but it also isn't pure. So we don't have this IO construct. We could make one, arguably, but it just a lot of people think it just kind of gets in the way. I think there are good arguments for both sides, but Rust has it has made its stance on whether this is an opt-in or opt-out kind of thing. So there we go. I'm going to try and define that function right here. Use data. Again, I always want to reach for that camel case. I'm just so used to doing that in Scala and Java. It's just force of habit. We'll take our validated form data. we're going to return... Actually, we're not going to return anything. We're just going to return unit. So at this point, they're doing more of this pattern matching stuff. Again, we don't really need to do that. I mean, I could explicitly have done it like what I was doing up here, where we actually pattern matched it out, but we can actually remove all that boilerplate and just say like form underscore data dot data, right? Like I didn't have to actually extract the string out. It's just that it's that's how you do it in Haskell. You'd actually do the pattern match, and it's a lot nicer here, obviously syntactically. Use data, I guess. Yeah, the only thing I can think of right now for this is just print line. So that's what we're gonna do. I don't actually need this semicolon here.
So Rust is not a pure language, right? Because this is a side effect that you're not sort of isolating like you do in Haskell with that IO unit that you return, right?
Yeah, you can just execute arbitrary stuff. So the main argument for why you might want to do this is so that you can like store programs in like lists, and then you can like execute them like X number of times, and so it gives you like composability as well. You can compose programs. You can think of programs as values, so you can do anything that you normally do with a value, but with your like entire program. So there are some nice benefits to using IO and like using this kind of functional effect system. There's a bit of overhead involved with it too, so yeah, it's just trade-offs.
Right.
So Rust made a decision not to do that. There are many functional languages that have made the decision not to do that. So what am I going to talk about? Oh, you'll notice that I put a little exclamation mark here.
Mm-hmm.
Rust has a... Are you familiar with macros or like X macros?
Just the basics.
So essentially, if you don't know, there are like macros in C and C++, and essentially, they just like it's sort of like a compile time meta programming. You can like generate code at compile time. It'll just replace this chunk of code. Oops. It'll just replace this chunk of code with some actual code that uses this value here. Rust style macros are a bit different from your X macros. They actually sanitize. Is that the right word? I think they kind of sanitize the inputs, sort of, in a way. Like it actually if you had a macro in, I guess, C++ that was like times 5, and then you gave it an expression like, I don't know, 2 plus 3, and if the macro was defined as being like, I don't know, this is a really bad example, this is not the actual syntax, but if you define the macro as just being like taking some kind of expression here and going like expression times 5, you can see where this would have problems, right? In C++, what that would do is it would just take this entire block of code, replace it right here, and instead of doing 2 plus 3 and then multiplying that by 5...
Order of operation.
Yep, order of operations, suddenly you got 3 times 5 plus 2 afterwards. So in C++ or C, this would evaluate to 15, and then you'd add 2, which would be 17, and then in Rust, because thankfully it actually is a bit smart about this, it takes the 2 plus 3, does that first, and then multiplies the 5. So Rust macros are a little bit nicer in that way. Obviously, you might think of that as a bit of a limitation. It doesn't let you do as many things as you might have liked to. There are other ways of achieving those kinds of things, but yeah, it's I can kind of see it being sort of a matter of preference.
Jonathan, sorry, I gotta mute the call for just 1 second. I'm getting a call from somebody. Okay, I'll be back on in just a couple of minutes.
Okay. So nothing else has happened. I didn't do anything.
Right. Okay. So we were talking about this exclamation mark and how it relates to printing stuff and macros and
Yeah.
such.
So print line is a macro. That's all I basically wanted to say. Print line is a
Okay.
macro. It takes some kind of string. You can also do like a format string with it too, like this, and then it'll put that in there. So if you wanted to put like an integer in here, you could print an integer, and that works. I'm not using integers or anything like that, so I can just directly do print line like that. So that's pretty much all there is to this. At this point, I think we can actually run this or compile it, see what happens. Oh, it must be a string literal, so I do actually have to do the format. So I can't get away with this. Oh well. And there we go. Everything compiles. So let's actually let's actually try and play with this a bit and see just how this works. Oh, another thing I want to mention is that there is pattern matching in Rust as well. It's not exclusive to Haskell and Scala. The syntax for pattern matching in Rust is actually the reverse of Scala's. So it's match and then form data, like that, and then you just go like I don't know, form data. There's no case keyword in this case. You just go form data string and then do the usual thing here. I think they're like separated by commas. I can't remember, something like that. Anyway, that's just wanted to point that out.
Okay.
So here we're gonna try and create a form data that I guess unvalidated equal form data. You'll notice that I don't give a type for this guy. This is because Rust is somewhat smart. It does some type inference. Oh, did I seriously do that? Okay, whatever. I'm just going to delete this. Rust is somewhat smart and does type inference. Haskell's type inference is really good. Scala's is pretty decent. Rust's is it's fairly poor, but it does exist. If I wanted to, I could be explicit though and say that this is a form data unvalidated, and that can help the compiler too because then it doesn't have to do type inference checking. But anyway, I'm just gonna get rid of it for now because it's a little bit verbose. I'm gonna give it a string. So here's my form data. It says, yo, what up? And we're gonna turn it into a heap allocated string with this toString method. Yeah, it's weird to see a string calling toString, doesn't it?
Yes, that is weird.
It's just because this is a heap allocated string. But anyway.
So really, it should be called toHeap allocated string, right?
Yeah, but it's like super long and verbose, so they don't like that. So that's the unvalidated form data. Now we're going to try and validate it. I guess, yeah, I just need to pass that in, don't I? Nothing to it. Maybe validated. And now we're going to use data with maybe validated. Alright, before I run this, what do you think is going to happen?
Okay, so what are we doing here? On the first line, we're creating a form data, and its single string member is going to be yo, what's up. It's going to be a heap allocated string.
Yep.
And then we're trying to validate it. What does the validate function do again? Can you see it again? I can't quite remember.
There we go.
So, if the length is greater than 8. So what's the length of yo, what's up? Sounds like it's greater than 8. Right? It's pretty close. How many characters is that? That's more than 8. Yes. So it's more than 8, so it's not going to be validated. So maybe validated should be none. And then we're going to print none. I'm not exactly sure how none is going to get.
So in Rust, there's there's a certain thing you can do. It's like an attribute in it's actually inspired by C# attributes. You can just say derive, and then you can go like debug, and it's basically the same thing as like implementing an interface for something, or like a default implementation. So debug is the same thing as like define some kind of like toString for this that will automatically print stuff for you.
Right. Okay. So are we going to do like a toString thing for none here or something?
Yeah, essentially it's going to create a...
Oh, so it's already done that.
Yeah, it already... some, or like option, the option type already has that defined for it. Oh, apparently it doesn't like that.
Yeah, so use data is expecting a form data, but it's not.
Oh yeah, that's right. See? I just tried to pass a form data, but we got an option back here.
Oh,
so.
type safety.
Yeah, type safety. There we go. We just prevented ourselves from doing something dumb. We didn't check what it was. We just wanted to take whatever it was and then print it. But
so it should take an option then, right?
Yeah, we could change this to take an option. They don't take an option here. We can kind of editorialize though. It's fine. Well, it doesn't really make that much of a difference. So,
I suppose then you kind of have like two checks where you're. Well, I don't know. I mean, I guess this is the trade-off for type safety, right? It might be slightly more verbose.
Yeah, well, we could just do an unwrap here, and then it'll just get the data out.
So get off my back, compiler.
Yeah, I have to do the unwrap here, actually. Yeah, I say, get off my back. In production code, you don't want to do this. This is a partial function. It'll blow up your code if it is none. Actually, I can't do an unwrap because... oh, yeah, so the thing here is that if this was a none, I couldn't call .data. That's a null pointer exception, right? Or null reference exception, right? So if I did the unwrap here, it would just blow up because that's exactly what I'm doing.
Could you create an overloaded version of use data, and then just have if the option is a validated thing, call this version of it, otherwise call this other version?
We could do that. Well, we don't. Okay, so Rust doesn't support overloading because overloading is actually a bit of an anti-pattern, at least in languages that support type classes. So in Scala, it's also an anti-pattern. In Haskell, it's an anti-pattern. There's a solution for that. There's a good blog post on that I should probably link. I'll put in the description of the video, and I'll send it to you a little bit later. That kind of illustrates why it's an anti-pattern. But yeah, they kind of, I think they do that a little bit later on in here. I don't exactly remember. But yeah, I could do something like that, but since we're getting an option, it's actually better if we use the feature that I just talked about, pattern matching. We can actually pattern match on validated, and we can say if it's a sum of some data, I guess, then we will print line, and it'll do pretty much what it was already doing, right? I'll just go, oh, maybe data's not a good name. Let's call it v data.
Maybe data. Possibly data.
vdata.data. So now we're actually allowed to do that, I guess, kind of dereference. Now, in the case of none, we're just going to print line. None. And this guy is just going to disappear. Both of these return unit, so the entire match expression will return unit, so I don't need to use any semicolons, or at least in theory, I shouldn't have to use any semicolons. Let's give that a shot. None!
Yay!
Yeah, so there we go. So yeah, there was a good example of how Rust can actually prevent you from doing stupid null reference exceptions and stuff too.
Yeah, that was cool. That's great. I like that concrete kind of example type thing. What if you just switch the direction of, switch it from greater than to less than, and let's see the other way for when we're actually validating it, like in the validate function. Let's just.
Oh, you want to actually just swap that around? Okay, sure.
Yeah, just make it less than or whatever, just such that it returns the actual value instead. Let's see what happens.
Yo, what up?
Oh, cool.
Yeah. All right, so that's this code in a nutshell.
All right.
The beauty of this is that we can define functions that work on all kinds of form data, but still can't turn unvalidated data into validated data. So essentially what that's saying is that, yeah, we can take a function on strings, and we can just do that function on any kind of form data. It doesn't matter what the type of that form data is. So let's say we represented form data as like two different types. We had unvalidated data and validated data, but we didn't have this like form data thing. So we had like just validated form data, unvalidated form data. Then if you tried to write a function for one thing, you would have to write the same function again for the other one, right? So that's what they're talking about here. They're saying you don't have to do that. You don't have to duplicate your code. Don't repeat yourself, right? That's what people say, and that's essentially what we're going to be trying to show off right here. So we're going to define this function lift string fun. So a bit of notation here. This is a function that takes a function and a form data, and then returns a form data. The way that you're supposed to read this is that it's using this principle called like currying. Essentially, in currying, this right here is the same thing as this right here. Well, it's not, okay, they're not identical, but they're isomorphic. So there's like a one-to-one correspondence between these. I might have talked about this before actually, but
those like currying, that does sound like something you've said before, but I don't actually remember what it is.
Yeah, so currying is basically this identity sort of between these two things. One way that I like to look at it is, or actually you can also look at it like this. The arrows are right associative, just want to point that out. This is not the same thing as this. These are not identical whatsoever. Just something I want to point out. If we think of exponentials, or sorry, I'm mixing up my wording here. If we think of functions as exponentials, so if I have a type from int to bool, like that, you can also think of that as bool to the power of int. And this mathematical relationship actually is a good way of checking this kind of thing, because remember, this is a product, right? This is just a tuple. So it's this guy is the same thing as going like a times b. And the way that I would look at this is as c to the power of a times b is equal to c to the power of b to the power of a. And as you know in math, you can. This is an actual identity, right?
Okay.
Are you following?
Yeah. I mean,
So,
it
like,
seems reasonable.
Like if I had
didn't
like
actually
2 to
do
the
that.
power of 3 times 4, it's the same thing as 2 to the power of 4 to the power of 3.
Okay.
And if we looked at it in this way, then what this would do is this would say, oh, this is c to the power of b to the power of a. And that is actually, maybe if I reverse these arguments, that's easier to read.
But I'm struggling to see how this applies to types, though. Sure, as a mathematical identity, I get you, but this whole like bool to int is the same as bool to the power. How can you raise a bool to the power of?
So maybe int is not a good example. If I had traffic light and enum, I don't know, traffic Like, I love this traffic light one. It has 3 colors: red, yellow, and green. I could have traffic light to bool, and that would be the same thing as bool to the power of traffic light. And why does this make sense? Because I can define a function from traffic light to bool. I don't know. Well, this is an anonymous function or something. I don't know. Essentially, yeah, let's just write these as anonymous functions. I can write a function from my traffic light, traf, and I can map it to a bool using pattern matching. So I could match traf, and then I could return if it's red. Actually, don't do this in Rust. You can actually make the same pitfall in Haskell. By the way, this is pseudocode. This doesn't actually compile. But this is a mistake you can make in Haskell as well. If you don't mark this as traffic light, it'll just match every case of this first symbol, because it doesn't. It basically treats this as like a wild card.
Ah.
Yeah, that's a gotcha. I've actually ran into that in Haskell myself. In Rust, you get a compiler warning about that what you're doing is dumb and bad, and it'll probably blow up and not do what you want. But yeah, it doesn't actually prevent you from doing that. But yeah, this is basically a way of naming like a wildcard normally. I'm not using it in that way, I'm using it in this way. It's less typing for me if I do it like this. So. But essentially I could do something like this, right? I go like red maps to true, yellow maps to true, green maps to true, and then I could define a second function, right? And this one may be false, and we can define it again, where now it's like this one's false, or actually maybe binary. This one's false. You can see where I'm going with this, though, right?
Yeah. So you're mapping each sort of enum of traffic light to a particular bool. So yes, that makes sense. Like I can see the left-hand side of that equation. So traffic light maps to bool, sure.
Yeah, traffic light.
But how
maps
about
to bool.
What about this whole bool to power of traffic light thing?
So remember that we like to think of types as sets, and the number of elements in a set is kind of like the numerical representation. So if I continued implementing all these functions, right? Remember, a function is also an object, right? I can pass this around. What you'd notice is that eventually, like, this is just like binary counting, right? We start with like 0, 0, 1, and then we go like 0, 1, 0, and then the next one would be like, I guess, 0, 1, 1. Oh, I'm sorry, I'm mixing up the notation. I guess this would be like 0, 0, 1. I was using trues as zeros, but so this would be like 1, 1, 1. This would be like 0, 1, 1. This would be like 1, 0, 1, 0, 0, 1. I could implement all of these, and the total number of functions that I would get is equal to if I took bool, which is 2 elements, to the power of traffic light, which is 3 elements, so 2 to the power of 3. And 2 to the power of 3, as we know, is 8, which checks out with this, right?
Right.
So we'd have 2 to the power of 8 different, or 2 to the power of 8, 2 to the power of 3 different functions. We'd have 8 functions in total if I were to go through this entire whole rigmarole.
I see, and just sort of exhaustively.
Yep, exactly.
Map all the different states to different bools.
Yep.
Okay.
That's the reason why you're able to think of this as an exponential. And that's why I'm able to say that this guy is not the same as this guy. So these two are the same, but these two are not the same. And the easy way to tell is by using the mathematical identities.
Okay.
Yeah, that's pretty much all this is. So, if I was doing this like this is not the same. Don't do this. Bad.
Okay.
Yeah.
Now, just one thing I just want to say before we continue on here. I do have to head out pretty close to noon.
Oh,
So if we
okay.
want to break this up into multiple videos or something, if there's going to be like a natural place to pause, just it may be getting close to the time of looking for that spot.
Okay, sure. So we're back. It's been a week.
Right. Okay. So the option can either be validated form data or none, and we need to check. Right. If there's some, we do this. Otherwise, do this other thing.
Yeah, I think
We're forced to do a null check basically here.
Yeah, I think ideally you wouldn't pass in an option here. Like ideally they'd want, or you'd want the caller to handle that, and then here you would just print like vdata dot, or I guess it wouldn't be vdata, it'd just be validated dot data.
Yeah.
So it'd probably be more like this, and I guess this would be an option, right? Or which one returns the option? Validate does. So this one's an option, right? It even says may be validated.
Yes, right, and then we pass the result into use data, right?
Right. So I think this is probably what they would want. Actually, I'm just gonna do this.
Okay.
I think that works. Yeah, because this is a unit.
Ooh. Oh, okay. So like for each thing, and maybe validated is not something you can enumerate over, right? Isn't it just a single? I guess it doesn't matter if it's one.
Sorry, what am I? Oh yeah, no, that should be right.
So you're saying like, okay, apply use data to every.
Oh wait, you're right. No, I can't do that. You're right because this has side effects. This is side effect encode. That's bad. I forgot about that.
Oh, because it does the print. Yes.
Yeah, that's a problem. You're right. That doesn't work. If it was a pure function, I could do this. It doesn't work though. If I
right, and just usually I think of map as iterating over a collection.
Well,
I suppose you think of a single element as a one element collection. It's just kind of a weird.
Yeah, like you can think of this as like a one element collection, and this is just empty list, right? Like that's not too different from, I don't know, like cons 1 nil and nil, right? Like that's not really, you can kind of see that these are roughly the same.
Okay, sure. Well, anyway, the important bit is that we're applying that function to our maybe validated result, or we would if the function didn't have side effects, but it does, so we're going to do it a different way.
Yeah, I'm just going to use plain old pattern matching. So
you're just sort of like inlining this function that you were using before?
Yeah, essentially. I'm not really a huge fan of pattern matching because it usually is more verbose than alternative methods, but for the sake of this, I'm just going to stick with something simple, and pattern matching is, well, simple.
Just briefly, what would be the alternatives here? Because we do need to check whether it's some or none, right? There's no way around that.
Oh yeah, no, certainly not. Alternatives would be, okay, let's actually try and take this seriously. Maybe validated dot unwrap or else. So in this case, if it's a none, it's going to return some other value. If it's a sum, it'll get the value inside of it. I think how we're gonna do this is, I'm trying to think, like how am I gonna like, oh, right, if we're doing a side effecting function, we have a special syntax for it. If let sum and I don't know, form data. Oh yeah, equals maybe validated. That's right. So if you're doing side effects, this is roughly the best solution that there is. If you're using pure functions, you can use map. You can use like get or else. I mean, sorry, not get or else. That's what it's called in Scala. It's called unwrap or else in Rust. Yeah. So this basically takes this guy, does a pattern match on it right here in line, kind of, and if it's a sum of form data, then execute whatever is in here. That took far longer than it really should have, but this will essentially do what we need it to do.
Okay, so. And
then otherwise, if you want to add an else case at all, then we could just say print line none.
So that would handle the case where maybe validate, or that would handle the case where we get nothing back, like a none back from maybe validated.
Yeah,
So,
this is the case where it's a none. Here, this is the case
Right.
where it's a sum.
Okay, well, I mean, to play the devil's advocate, I think that's the same number of lines as the previous.
Actually, you're probably right. This isn't really that different from just doing pattern matching. Pattern matching is, yeah, you're right. You're right. This is actually probably more verbose than doing pattern matching. But if you wanted to do something only if there's like a only on some and then just, you know, do nothing in the other case, then this works. And this is slightly less code. The combinators usually work a lot better when you're working with pure functions, I'll admit. So yeah, pattern matching here is probably just as good. Yeah, there's nothing wrong with pattern matching, by the way. It's not like an anti-pattern or anything. It's just that sometimes it can be a little bit verbose compared to the alternatives. So at this point, use data essentially is using the type parameter here to ensure that any data that we pass in is already validated. So there's no way to call use data on this like unvalidated, for example. So if I tried to do that, it should fail to compile. Yeah, see? Expected struct validated, found unvalidated.
So basically, hey, you didn't check that this is null, and because this is Rust, the default is you need to check things for null before you use them.
Well, this is well, I mean, not even that, but like even if we didn't call validate at all, and there wasn't this like option whatever, right? Like this function signature is taking advantage of the type parameter that we're not really using. Like the type parameter isn't really, it doesn't technically exist in the struct, but it can be used for type checking. So we can't pass unvalidated form data into use data, right? That's kind of the point of this. I mean, yeah, there is this whole...
to avoid a null reference exception, right? Because it's possible that unvalidated could be essentially null if we fail to validate it, right?
Okay, I mean, if we want to consider all this stuff, then yes. I mean, that's the whole point of all this. This is to avoid null reference exceptions or null pointer exceptions, but what I'm saying is, like, I could have just taken a form data, right? I could have just removed this type argument and then changed this function so it doesn't return like a sum or none or anything like that. And then we just have this function that takes form datas, right? But then you could also take unvalidated form data here. Do you see what I mean?
So, okay, because it's a generic class, you could put whatever you want as the type for form data.
Yeah, exactly. Well, yeah, that is right. But in this case, this one requires that it be validated form data that comes in.
Because we're using one of the members of validated, or... Oh, no, never mind. Well, hold on a second. Yes, we are using one of the members of, like, the... blur words. So we're passing in validated, which is an instance of form data.
No. Validate is not an instance of form data. Validate is just a struct. It's just some random thing. It could be foo.
But aren't we typing it by saying colon some type?
Oh, you're talking about this. Sorry.
Yes.
Yeah, this is an instance of form data validated. So
Right. So
right.
that, like, we could. I know you're not a huge fan of overloading stuff, but we could theoretically have another function that takes form data unvalidated or form data.
Okay, yeah, this is the point that I wanted to come back to, because this was because I said this was an anti-pattern before, and then I posted like a Scala article, and that's not very good.
Specifically, overloading is an anti-pattern, or
yeah, specifically overloading is anti-pattern. We're gonna tangent.
Okay.
Overloading is bad. Consider the following function. We're going to call it identity, or just ident, because I'm lazy as hell. And it takes an A, and then it returns an A. You've probably seen this before. It just does that. And you can pass it anything, and it'll return exactly what you gave it, right?
The identity.
So, yeah, this is an identity function, right?
Yeah.
So, generics in Rust work in a very particular way. This doesn't actually... This is actually a family of functions, and none of those functions exist right now. But let's say I want to call ident.
You just wrote like. Hold on a second. Didn't you just write a function? What do you mean none of the functions exist?
Allow me to explain.
Okay,
So
okay.
I'm going to pass it, I don't know, 2 as I32. Oh, you don't have to do this. I think you can actually just go like 2 I32 and it'll just consider that an 32-bit integer. Essentially what this is doing is it'll give me back, this is pseudocode notation now, it'll give me back that same integer, right?
Whatever it accepts, it will return.
And if I did the same thing with a boolean like true, it would also do the same thing. But
right.
What Rust will do is it's actually going to rewrite this as ident I32, and then it'll replace. It's basically just going to replace the argument with I32. In fact, we could probably just get rid of this.
So it will sort of overload for you, like there's special syntax.
Yes, this is something called monomorphization. So as you call this function, Rust will automatically monomorphize the function for you and generate these specific implementations. So, yeah, it's just going to do this a whole bunch of times for every single call to the function. So if I didn't call the function at all, these functions wouldn't exist. But because I'm calling it with these arguments, it's going to auto-generate these. So that's why.
Do you have any idea if other languages take a similar approach? Like if I write a function that takes some generic type.
Yeah, think about this in C#, for example, right?
Yeah.
If I wrote this,
same,
it's roughly the same thing. It's just monomorphizing it into each of the individual functions. But as you've probably recognized, this is the same thing as overloading. Why would I do this when I could write a single one of this? Like, let's imagine we have 10 different types that we want to pass into this function, right? Suddenly we have 10 functions. But I could have just wrote it as just one function, or a family of functions.
That makes sense in this case.
Yeah.
There might be a case where you only want to handle, say, 2 types, right? Like it's some complicated class.
I mean, okay, yeah, you could say that I suppose you could make the argument that you might want to overload in that case, but
you basically just want 2 or 3 or whatever. Right?
Yeah, but then there's another problem with that. What if I wanted to? Okay, let's change this to something a little bit more practical. Let's call this convert to JSON, right?
There. Now we're talking.
And A is a JSONable.
Oh, okay, so it implements some interface so we know it's going to have whatever requirement.
Yeah, essentially. So this will return, I don't know. It'll take something that's JSONable and it'll return like a JSON object of some sort. I don't know.
Whatever. Yes. It'll basically return JSON, represented by some special JSON object.
Yeah, there's some implementation in here. We don't know what it is. Yeah. What if I wanted to now take that JSON object and then print it? Do you see where this is going? So now I have one for int, convert to JSON int, convert to JSON bool, and now I have to add a print JSON int, right? And then I have a print JSON bool.
Well, I don't know. I mean, you would think that the JSON objects would have enough in common that you could have a single function that's just going to print out the JSON. But I mean, that's a particular of this example. I'm sure you could think of another example.
Yeah.
It's just JSON, right? I mean, it doesn't matter if there's
I guess you could certainly make that argument, but like, it could be a different example, right? And
yeah, right,
what would be better is if you just had like a generic print here, like a fun print JSON that took like some kind of type class that implemented like JSON or something like that, and then did whatever instead of having, because essentially you have instead of having to write just 2 functions, now I have to write 2 times 2 functions, and then if I run another function that calls into this, then I have to write another additional 2 functions. So instead of having like 3 functions, I have 2 times 3 functions. I have 6 functions. So it just kind of multiplies.
Okay. Let me do an example, and we can talk through it together. So say I have Okay, so say again we want to print something, and I have two classes that I essentially want to print out so that just the user can see the relevant information. I have like, um, let's see here. Maybe I have like, I don't know, some complicated form. Like I have like some like tax form A, and I have like, I don't know, a company report, like an earnings report or something like that.
Okay.
Right. So I basically need to do the same thing for both of these classes. I need to go through and I need to pull out, I don't know, whatever kind of common information. Like maybe our goal is to make sure that some of the information on each of the forms matches or something like that.
Yeah. Okay.
So in that case, like, you know, you would basically be doing the same thing to each of the forms, but it would be like a tiny bit different. So maybe you could have two overloaded, you know, print tax form functions that would take like an annual report instance and like a T4 whatever instance. Like I would say in that case you would not want something that would take just a generic type. Maybe it would be better just to have two overloaded functions that would handle this case. I don't know. I'm just kind of
I'm not really following. So you would just like pass. I am curious to know like what you actually mean.
I'm just trying to think of a case where it actually would be appropriate to have two overloaded functions.
Well, overloading is it's a mechanism for achieving something called ad hoc polymorphism, and that's the same thing as what a type class or what an interface basically allows you to do. So
Right.
they're basically two different solutions for the same problem. It's just that, in general, it is largely considered that overloading is an anti-pattern, at least in functional programming circles, because you have this interface, this type class ability, and it also, if you think about it, if you were to have like some different implementations, for example, for each of these functions, you know, like if you just refactor this to take an interface which only uses the common logic, then you also gain inversion of control, right? Because now I can pass the correct implementation in. Like this function doesn't need to change anymore. It's generic. It's completely polymorphic. But
Right.
right, it gives you. Do you kind of see it?
Yeah, I think I see it. I mean, it's not the fact that you have one function that deals with multiple types. It's that it's the anti-pattern is if you're specifying concrete types in different.
Yeah, exactly. If you specify concrete types, then, well,
then all of a sudden you're going to be repeating yourself.
exactly. You're going to be repeating yourself, and also you're going to lose that inversion of control, right? Like dependency injection. That's a big deal. People care about things like that. We want to make sure our code can scale.
My contrived like tax form example, then it would probably be better if you just had some interface or something that would be like printable tax form.
Yeah, exactly. You would pass in an interface. I mean, in that case, you really aren't just overloading. There really is no point in overloading.
Right. I mean, I don't know. In some ways, it's kind of like, I don't know. It's kind of just like a semantic issue, right? Because we still kind of we are doing the same thing. The goal is the same. It's just which is less verbose, which is going to be easier to maintain.
Yeah, exactly. And this is a lot easier to maintain than overloading, because now I want to add what if I want to add another type? What if I want to
generic that implements a particular interface or something like that? I think that totally makes sense. That we would want.
Yeah, it's not specific to functional programming at all. This is just the same thing as like, well, it is just inversion of control, dependency injection. You want to pass in interfaces, right? You want to program to an interface. That's literally all this is about.
To further derail this talk that I
okay, go ahead.
Like, crap, now I just forgot the buzzword you said. What is it again? You want to program to an interface And what was that, like, that thing that I hear bandied about all the time, like inversion of control?
Inversion of control, dependency injection.
Yes. Could you go over that a little bit, because those are terms I've heard before, but I can't really define them.
Oh, okay. Well, I mean, dependency injection is basically like I have a function, it requires something, and I don't have access to it. How do I get access to it? Right? Like, usually programming to an interface means that you're like passing around interfaces instead of concrete types. So, I don't know. Maybe we have something that like goes to like a SQL server or something, and then it fetches data, and we want to test that, right? We could have a production version of the SQL fetcher, for example, and we could also have like a test implementation, but we can't call this function on both of those unless we take some kind of interface that SQL fetcher and test SQL fetcher both implement. That's
Right.
essentially the point. It's so that you don't have to change your logic. You can just pass in different. You can pass in different implementations, and therefore you get testability. And this is very important, obviously, if you want to write unit tests and integration tests and whatnot.
Like that term of passing or no, that's programming to an interface.
Mm-hmm.
So what about dependency injection?
Well, dependency injection basically is I need stuff. How do I get that stuff? And I don't really know like an easy way to describe dependency injection other than like this is your dependency, right? A in this case is the dependency, and you want to get certain dependencies so that this code in here can run. So dependency injection and dependency injection frameworks are all about how can we make it easy for people to get their dependencies to their code that such that they can actually like easily test their code or like swap out different implementations and stuff, right? And that's what programming to an interface is meant to help solve. It's this problem of, how do I get dependencies? So that's kind of the gist of dependency injection.
Well, I definitely get programming to an interface. I still am not super clear on dependency injection, but maybe we should move on and get back to the
Yeah, we can. I feel like that's kind of outside of the scope of this talk. Yeah, there's a lot of there's no like single solution for dependency injection. There's a crap ton of dependency injection frameworks and stuff like that out there. So yeah, it's not an easy problem to solve, I guess. There's no like one unified solution that everybody has kind of agreed upon is the best way to go about it. So it also kind of depends on the scenario. Anyway, that's enough about overloading and dependency injection and whatnot. Let's talk about this lift string function thing. So I don't know what I'm doing. I kind of like scrolled around and I lost my place. We were trying to implement this function. I think it's like a higher order function. It takes a function from string to string and returns. Oh, it also takes a form data. That's right. And it returns a form data. Oh, and this is interesting. This is actually polymorphic. So this will take any form data. What's it going to do? It's okay. Here's the actual implementation. It takes a form data. It does a pattern match on this, and then it creates a new form data with the function applied to the string inside. Okay, right. That generally roughly makes sense, I think. So the way that this would be done in Rust is we'll take our fun. Actually, let's just call it F. I don't really want to call it something that's already a keyword in the language. It's a function from string to string, and we're going to take a form data of type A and give it a name. Let's call it form data. Sure. Yep, there we go. Just making sure that I've written everything out here. And we want to create a new form data, apparently. Okay. So again, we're going to have to probably turbofish this, I think. Actually, we might not have to. So our phantom is just going to be called, it's just going to be phantom data. And then our data is just going to be f applied to our form data dot data.
Don't we have to check that the form data is actually going to have some, like whether it's going to be some or none?
No, because the form data itself is not some or none, right? It's only if it's an option form data. So the option wraps the form data. So we don't have to check that.
Oh, right.
So this is...
So that's only if it's like if the type of form data is validated, because then...
No. This is polymorphic, right? This takes A. So form data is going to be any kind of form data here. It could be unvalidated. It could be validated.
Okay, it could be anything.
Yeah, and this is not
option.
Yeah, it's not option either, right? There's a difference here. This is option. This is not. So this is basically assuming that we either haven't validated yet, or we've validated but we've already handled the null case. That's essentially what this is doing.
Screensaver just turned on. Okay, there.
Oh, okay. So this is going to essentially map some kind of function from string to string onto our form data here, and I guess we could try and implement that. So I'm gonna have a function. Oh gosh. Actually, I'm just going to do it as a lambda. I feel like that might be easier. We're going to take our unvalidated. Actually, can I do that? Probably not. Okay. Because use data... Okay, so here's where move semantics come in. If I moved unvalidated into the validate function, which I am moving, then I can't reuse it. So what I could do is I could copy it. I don't think that would be too difficult. So I've already explained this syntax before. Essentially, this is going to define sort of like a copy constructor for this. I have to be explicit that this thing is going to be copyable, and the only stipulation is that anything inside of this is also copyable. So if I do that, if I pass in unvalidated here, because it's copy clone, I should be able to reuse it. So if I wanted to lift a string function here, such as, I don't know, we're going to have a, which is of type string, and we call like a dot, I think it's like to uppercase. Oh yeah, this is the closure syntax. It's kind of weird. We use these like bars. It comes from Ruby. So if you're a big Ruby fan, yay. We're going to pass our form data here. I'm going to give the unvalidated one since that was what I was kind of going with already. And this should return our unvalidated form data in uppercase. In fact, I'm just going to go ahead and do a print line here. I'm going to take upper.data. And I think this should work. I'm not entirely sure. It cannot be implemented because field does not oh no, string doesn't implement copy. Yeah.
Really?
I think it might be because, well, this is a heap allocated string, right?
Oh, right. There's this.
Yeah. So maybe that's not going to work. I could give this a reference. I'm just going to ignore that for now. I feel like that's...
why couldn't you copy a heap allocated string?
Oh, you mean like just clone it? I could clone it. Yeah, that's
So you're saying each of the members must be copyable in order to implement this copy constructor that you wrote up with the weird syntax up at the top.
yeah.
Right. So the
This
string also needs to be copyable or
yeah,
clonable.
a string needs to, they basically need to do something like impl copy for string and then
So what is the solution to this problem then? If we did want to have a copy constructor for our form data, and you needed to have some is there any way that you can sort like what's the terminology in C# where you're basically writing an extension for a particular type? Like you could write some function and then attach it to string in sort of an artificial way.
this is called a type class. So, or sorry, not a type class. Sorry.
So like,
In Haskell, it's called a type class. In Rust, it's called a trait. So I could define like a trait copyable, right? And then I can give it. It's sort of like an interface. I can give it functions like foo that returns.
But
like,
even though string is a built-in type, you could still sort of give it this trait that it is copyable.
yeah, I'm okay. Let's get this to a point where it can compile again, and then I'll show you something kind of silly. That should be fine. Yeah, I can create a trait called like I don't know foo, and it has a function that let's call it foo, and it takes I don't know let's just say it takes self and returns I don't know I32. I can actually do something like impl foo for I don't know u size, and I can actually like define foo for the u size as I don't know self as I32. And this is basically just like cast this thing to an I32. I could also do something like I don't know multiply by 2 and then cast as an integer 32. So if I have a u size, we'll annotate it. 32. I can actually go blah dot foo, and if we print this, then it should just show up. Oh, that's right. Doesn't have a size known at compile time. Oh, that's a good point. Okay, this should take a pointer to a function or a reference so that it's actually sized. There we go. See, it now prints 64, and we basically all we did was we extended u size. In fact, if I wanted to, I could have specified that this was like a u size, and then just called foo on it right away.
That's pretty cool that you can change things even if you don't have access to the.
Yeah, that's why extension methods exist.
Yeah, well, it makes sense. I just was curious how Rust does that.
Yep, this is their replacement for interfaces. So rather than having two separate features, interface and extension method, we just have it all wrapped up in a single feature. So anyway, this should. I don't remember how much of this I wanted to comment out or how much I wanted to keep in. I think if we're gonna be calling unvalidated, or if we're gonna be using unvalidated, we should just comment this stuff out for now. I'm lazy. I have a mismatch in types. Oh right, it expects a reference, and I'm not passing a reference. So this should be adequate. Yes, that works. Yo, okay, what up?
So you were passing by value before? Like what is
I'm just
thinking like how this works for a function.
I was trying to pass by value earlier. Yeah.
So you're trying to pass a closure by value?
Well, actually, I think we still could. We don't have to pass this by reference. What we could do is take an f and then specify that f implements this, and then...
So it implements a particular signature?
Yeah, this is actually defined as a trait, or like an interface, basically, if you want to think of it in object-oriented terms. So I think that actually does work. Yeah, that does work.
So I still am struggling to, like, for passing by value or by reference, I've seen that in the context of like data, and that making it a different. That's determining whether or not you can sort of change the data inside the function and have that change reflected once the function returns, right? If it's passed in by value, you're passing in a copy and changes aren't persisted.
Right.
Passing by reference, changes are persisted. So how does that work when you're dealing with passing in a function?
When you're dealing with passing in a function?
Yeah, like, so you were passing in that function by reference or to fix that compiler error, right?
Yeah.
You had to put in.
I passed it by
in the context of a function. Like, why would that matter? What are the possible implications of passing in a function by reference or by value?
Well, a reference, as you know, is like a pointer, right? And a pointer has a fixed size. So, essentially, sometimes you want to make sure that the data that you... okay, if I were to do something like this, it would actually be taking what is called a trait object. And what trait objects do is they allow you to basically do like dynamic dispatch. I don't really want to get too into like static versus dynamic dispatch right now, but I guess it's kind of important to explain that in the case of this. Basically, I can't easily just pass in. Let's say I have like a list of, I don't know, shape. Like, this is a classical object-oriented example. We have shapes, and we want to pass in different shapes, and we want to call different functions on different shapes, right? But in Rust, everything in the list actually needs to be the same size in memory. Otherwise, you can't execute these different things. So normally, what most languages might do to solve this issue is just, allocate on the heap, just have a pointer to something that, implements shape. But in Rust, we're very explicit about everything, right? So Rust actually allows you to store everything in a list and have everything be... it doesn't actually have to be hidden behind a pointer, as long as it all is of the same size. So this is basically a way of saying, okay, I instead of giving it a reference here, I could have actually given it like a box pointer, and it would have been fine with that as well. So if I did this, I could have heap allocated the closure. I could have boxed the closure and passed that in, and Rust wouldn't complain about that. But if I wanted... Okay, yeah, go on.
Okay, so the distinction with, like, when you pass in a reference, like you say, you're passing in a pointer, which is usually just like, a 32-bit integer or something like that. So when, like, you are passing this closure in, like, it's not defined outside the function, right? It's just defined inside the function invocation, right? So,
like this one here.
Yeah. So you're just defining that right there.
Yes.
So if you put an ampersand in front of that, it's not passing a function in somehow, it's just passing in a pointer to the function. Like,
exactly.
Somehow,
yes, and that has a fixed size.
Where
so
is that function stored then? So it's stored somewhere outside of, like, you don't have it stored in a variable. I'm kind of confused about, like, where the underlying data is.
Oh, what I'm...
Just allocated.
It's not allocated on the heap. This is actually allocated on the stack. I think what this desugars to is something like let, I don't know, a equal this, and then pass a in by reference. Yeah.
Oh, okay, then that makes more sense. So
it's sort of like an anonymous reference, I guess, to
right.
this thing.
Okay.
It's syntactic sugar, basically.
Right.
So you're borrowing the closure instead of actually moving it.
Okay, so if you pass it in by reference, you're passing a reference to that sort of hidden variable that the compiler will create down the line. So if you pass it in by value, you're actually going to the location that we're storing the bytes associated with this function. We're copying those bytes.
Actually, we don't have to copy those bytes at all.
Isn't that the definition of passing by value? Like you're passing in a copy, so that changes will not persist if you make
we're not. Well, it's not passed by value in the traditional sense, right? This moves the value. There are move semantics here, so we can move the closure into here if we specify that we're taking in is some generic f that implements this trait fun from string to string. So now I've moved this closure over. I don't have to allocate any additional memory for this. If I tried to, let's say I bind this to a name explicitly, like let x equal that, I could pass x in here, right? But if I tried to print, I don't know, like if we called x on this down here, we would get a compile error because x was already moved into here, and then after it got moved into here, it got deallocated at the end of the scope because we don't need f anymore.
Interesting.
So that's what ownership is about. So lift string function takes ownership of f, and then at the end of the scope, it just deallocates it. So
you're literally changing the location that function is stored at. It was stored at location A before you moved it by passing it into this function.
Yep, exactly. And this is the same thing.
That location in memory, move somewhere else, and then after this function returns, it deallocated.
Yep, exactly. So the reason why this is a compile time error is because this is now a dangling pointer, right? Because we've moved this into here, it's been deallocated. If we try to dereference some memory that has been deallocated, for all we know, we could allocate some more memory in between that would overwrite that memory slot. Then dereferencing x all suddenly, doesn't work anymore.
Okay, so and I imagine there would be some performance implications if you had some giant data structure. You would want to be careful about whether you're passing it in by reference or not.
Yes, exactly.
If you have to move that whole thing, that could be pretty slow.
Yep.
Just a pointer to the thing.
Yep, exactly. And it's like this in C++ as well. There are move semantics there. If you pass in something, it'll like move it, for example, and then I don't know if the compiler is smart enough to detect use after free like that. I think it might just allow you to just reuse stuff in C++, but in this case it doesn't.
Right.
Yeah, that's that.
It's been a while since I've coded in C++, but my recollection is passing something by reference is just the way you described.
Mm-hmm.
But if you pass something by value, you're not moving it. Like it's just creating a copy and passing that.
No. Well, okay, that's in C++. Remember how I was talking about traits and like how you could do this like a sort of derive. Oh god, let me type it. Derive, copy, and clone, right?
Yeah.
If you're passing around something by value and you're expecting it to create a copy, it's basically because it implicitly has a copy constructor, or maybe you have to define a copy constructor for it in C++. You can't just do that for any type. Like integers in Rust, integer already implements copy, so I don't need to do that. I know that anytime I move an integer into a function, it's going to call the copy constructor.
So
I think it does move it unless you want to reuse that same variable. If you reuse the variable, then it'll actually do the copy. I think.
Right. Yeah. If you try to use it after the function invocation, because we're doing this copy rather than move, if you try to use it again, it will be fine with that.
Yeah, exactly, because we did a copy. So you should always be explicit about like, are you using a copy constructor or not? And the way that Rust does it is you can either derive it or you can actually manually do the impl for it. Like you can do an impl copy for whatever type, and you can just do it yourself. Obviously, it doesn't work in this case, but at least not without a little bit more effort. But yeah, that's the kind of behavior that you're describing when you mean like pass by value and it creates a copy. It's calling the copy constructor.
Right. Yeah, that makes sense.
So anyway, after going through that long tangent, we've discovered that we can write generic functions that work on any kind of form data, whether it's unvalidated or validated, and that's what this is all about. That's cool. What's this about? Data to upper. Okay, I basically just did that. I'm not going to go through this. This seems kind of pointless. And then here they're talking about type classes, where we can choose different behaviors, conditional information that is non-existent at runtime. So this kind of goes back to what you were talking about with overloading. So what we could do here is we could say impl. Okay, well first we're gonna have to define a trait called sanitize. So here in Haskell land, they specify a type parameter here. We don't have to do that in Rust because we have this sort of object-oriented notation. We can just we can create this function called sanitize that takes we can say it takes self, and then it'll return a form data validated. And so if we wanted to, we could impl sanitize for form data. We want to implement this for specific instances of form data. We don't want to implement this. So what you could do is you could go like, oh yeah, I want to implement this for all the form datas, but in this case, that's not really desirable. We want to implement sanitize. Sorry.
Is a trait like completely synonymous with an interface in Rust? Like, are those basically, because you're saying like anyone that has a trait?
They're synonymous up to the point where, like, you know, like the limitation of object-oriented programming, right? Where you have, I don't know, form data extends sanitize, right? If I don't own form data, then how can I change its definition to extend my trait sanitize, right?
Like, use extension, at least in C#.
Well, yeah, of course. In C# you'd use like extension methods, and I don't know if Java has extension methods yet or not, but the traditional OO that doesn't include extension methods can't really deal with this. I mean, I guess neo OO, as I like to call it, probably you can do stuff like that. So yeah, you can kind of think of it as being synonymous with an interface. There's nothing wrong with that. I think older literature for Haskell actually compared type classes to regular OO classes, and I kind of see it, but it just maps better if you think of it as an interface rather than a class. So anyway, we can certainly write stuff like, oh yeah, we want to create a validated form data here. So if we want to do that, what we're gonna have to do is so by the way, there's different notations for self here. There's obviously the self, there's self by reference, and then there's self mutable by reference. So this takes a mutable reference. I'm gonna just take self. I'm gonna move it because I'm lazy and I don't really want to do. Actually, it might actually be easier to work with if I pass by reference, but we're gonna move. So what they're doing here is they're gonna do a pattern match on form data, I think. I'm not gonna bother with that because I can just call self.data, and they're calling. Oh, okay. They're doing this filter for is alpha numeric. Obviously, if you're gonna sanitize a form, this is probably a better algorithm, but I think we said that our definition of invalid form is
if it's less than 8 characters or something.
Yeah, so it has to be at least 8 characters. So if we want to sanitize our data, I guess what we could do is we could like append 8 characters. So how do you This is something I'm
Just,
actually
can you
not
just say
sure.
like plus food?
Yeah, I think you can do something like that. I think
Like
Rust doesn't have a concept
concatenate.
of. Rust doesn't have like a plus operator for strings because of the whole like keep versus stack allocated and.
Right. Well, you could just return a static string that's like food.
Yeah, we could do that. We could certainly do that. So I could. Uh,
There you go.
yeah, I think that'll concatenate. I actually don't remember. This is starting to go into the edges of my Rust knowledge, which is a little bit sad considering that it's just string concatenation. But yeah, the Rust can be a bit complicated at times, and this is one of those times. So it's the price you have to pay for having a lot of control over everything that you do. So I think, alright, so our phantom in this case is going to be of type validated, so we're gonna turbofish this guy. Phantom is phantom data, and our data is going to be this data. And I don't actually know if this works. I might actually have to do a toString here as well, just to be safe, because I'm using heap allocated strings. And that should theoretically compile. Oh wait, right. I'm being silly. That's not how this works. You have to go like this. So if I wanted to insert a comma between them, I could have done this, but no. I'm just going to do.
Oh, this is just like printf, right?
Yep, this is exactly. This is just like printf. That's Rust's solution to string concatenation, which is, yeah, it's not the prettiest thing in the world. But yay, that works. So if we wanted to sanitize that, we could. And of course, in this case, they're implementing sanitize for validated as well. And as we know, that looks something like this. What they're doing is they're using the identity function. That's why it's called ID.
Yeah. So you're just returning it. So it is it's validated. So I guess sanitize could have different.
Yeah. So you could if you wanted to sanitize already sanitized data, then you can return just the data you already had. So yeah, this is how you would essentially do overloading for your form data. And by overloading, I mean you're literally just programming to an interface. This is an interface.
That's overloading in kind of the bad way, because we're specifying a concrete type, right?
What do you mean?
Well, so we were talking about. Hold on a second. Let me just look at this. So we're implementing sanitize. So this function, if it's not validated, we add a bunch of characters. If it is validated, we just return itself. Right? So what I mean is that earlier we were talking, it's best to pass in, a generic class that implements some interface.
Well, you have to give an implementation at some point, right? You can pass it in the interface, sanitize. So I'm going to take an interface that I know, like maybe I take in an A that can sanitize.
Okay. I think I see what's going on here. So what we're saying here is we're basically saying form data unvalidated implements the sanitize interface.
Yes, this implements this interface. This implements this interface.
Yeah, okay, that definitely totally makes sense. So now we have this generic thing that you can pass any form data that implements the sanitize interface.
Yes, exactly. So that's essentially what's going on here. Do I need to do a concrete example here, or do you think you're okay with that?
Actually, that might be a good place to sort of finish off today. Like I said, I have to go at 11, which is a few minutes ago.
Okay.
Can we just do
Well, let's do a wrap up, because I don't think there's anything else here that's really important. Like there's this example, which I guess if we want to translate it, that could be like a homework assignment or something. I don't really think it's that important that we go through this. I just wanted to do a quick wrap up on this. So now we know what a phantom type is. It's basically a type that with an unused type parameter. What do you think? Of phantom types. Do you think they're useful? Do you think that people, should try and incorporate them in their code more? Like, just give your thoughts.
Well, to be honest, this talk has been very useful for me to understand sort of like the best way to overload, which is not to add constant types, and I learned a lot about options, and it's very good. But I don't feel like I learned that much about phantom types. They still seem like this weird sort of dangling vestigial thing that we could just kind of snip off because we don't really use them.
Yeah,
Right?
I
That was
can.
form data. If you just get rid of that phantom type, wouldn't all this just work basically? Because we're only using the string.
Well, the whole point was that things like, say, where was it? This guy, use data, takes a validated form data, right?
Right.
And we can only ever pass in validated form data. So what the phantom type is trying to do here is it's trying to give you type safety. It's trying to make it so that if you tried to give this thing an unvalidated form data, it would just fail to compile, period. Do you see where this is going? So that's kind of what the point of it is.
But by instantiating a form data that is typed as validated, wouldn't that also give us the type safety even if we didn't have that phantom data inside? Like, if you just got rid of phantom data and then instantiated form data that's typed as...
Oh, like having like a... Yeah, I was thinking about that, like what if we just had like a trait or something of form data, and then we just had like two, I guess, almost like subclasses, like validated form data extends form data, or unvalidated form data extends form data. Like you
Right,
could do something like that.
exactly, right, and then you just have your class implement that
Yeah,
interface.
I feel like that's a very object-oriented solution, and I think it does work. In fact, you could even do form data as like an enum, right? You could do like an enum
Yeah.
form data, and then have a validated one and an invalidated one. I think there are trade-offs to that. Like obviously, it'd be harder to do stuff like the generic functions.
If you just got rid of that phantom type, but you still left it as the generic A in there, would that not compile? If you don't use the type somehow?
Sorry,
Like if you just get,
I didn't quite catch
like
that.
if you just delete phantom there,
Oh,
if you
like
just
this
get
guy?
rid of that, yeah, but you leave it like that with you're still typing it as some generic.
Oh no,
type A.
this is what we wanted to do originally, but when we ran this, it didn't compile because it just said, "Oh, the A is never
But you're
used." It
not
said,
using it. Oh right, okay.
"Yeah." So this is actually a hack to work around
Yeah.
that.
Honestly, it does feel that way a little bit. It seems
Yeah,
kind of
well,
like,
at least in Rust, that's how you would do it to hack around
it's
this
like,
error.
the compiler really doesn't want me to do this, but I think I'm just going to do it anyway.
Yeah. In
So,
other languages like Haskell and Scala, they actually let you do this, so it's a lot more ergonomic, and it does feel a lot more like, yeah, it is intended that you be able to do stuff like this. But if it's like, actually, I don't know how C# behaves. Maybe C# allows this as well. But if you wanted to do it in C# and it didn't allow that, then you could also create your own dummy phantom here. You could just make your own phantom data. Do it yourself. DIY phantoms.
right, and I mean, I of course, coming from an object-oriented background, like, other solutions do pop into my head. Like, if you just don't want to type this at all, you could just have, your form data as a string that you could pass into some function that would check whether or not it's valid, and if it's not valid,
Oh, like do like a smart constructor kind of thing, and just have it return like
yeah,
a sum or
right.
none kind of thing. Yeah,
So,
you
like,
could certainly
the
do
goal
that as
here
well.
is to essentially take a string, determine if it's valid. If it's not valid, do something to it to make it valid, and then return the validated string, right?
Yeah,
Like, that's
yeah.
what
You
we're trying
could.
to do.
I can definitely see arguments for that.
Right.
I'm gonna play, I guess, devil's advocate here, or maybe I don't know. I'm gonna say that what is cool about phantoms is that they don't take up any space in your struct. So if I wanted to do a struct with like a flag here that was like, maybe this was like a, let's say there was like a validated flag and it was like a boolean or something, like that takes an extra bit or whatever in this struct. So if I had like a whole bunch of form data, I'd have all these flags, and maybe I don't want it just to be two different variants. Maybe there's like validated, unvalidated, and like, I don't know, sanitized or like uppercased. They could have even more variants, and then it'd take up even more memory. Actually, would it? No, not really. But I mean, like, you have this extra bit of information here, and you don't need that if you're using a phantom, right? Because the phantom is a zero size type, as it says over here,
But
and it doesn't take any
there, like,
memory.
there must be some additional memory cost of even having a generic type here, right? Like typing it as something, doesn't that incur some sort of overhead? I mean, like a Boolean flag is literally just like it's a bit, right?
True.
It's zero.
Well, no, there's no cost for this. The types only exist at compile time, and after it compiles the code, the types don't exist. It does type erasure, so it's literally just bits and bytes at that point. So
Right.
I think you could make an argument that yeah, it's zero sized and that's cool. Here's another example that they use: unused lifetime parameters. So if you're using Rust and you have these like lifetimes here, I guess you could use phantom data for that. I've seen some kind of clever usages of phantom data in like the iterator implementation for Rust, where they use phantom data to like pass in a type parameter for something that doesn't that takes a type parameter, but the type itself doesn't really want to have a type parameter. So I guess that falls under unused type parameters. Here they talk about ownership and drop checks. I don't know. I don't really want to get into this. I feel like that's too nitty gritty.
Well, like,
but
why would the people that write the Rust compiler not just allow this kind of behavior if it's something that people really want, and they're going to the trouble of coming up with a kind of like unergonomic
like
workaround?
an unergonomic hack around this?
Yeah, I wasn't going to say hack.
You know, honestly, I don't know the answer to this, and maybe someone can correct me if I'm wrong, but I think what probably ended up happening was they added this error for not having anything, or they added this error first, and then Rust got stabilized. It went into 1.0, and then someone realized, hey, you know, I want to really use like phantom types like I do in say Haskell or Scala. Why can't I do that? And they said, oh no, we don't have a way of doing that. So they ended up basically creating this solution sort of for backwards compatibility. So this is kind of a don't break the language's semantics, just add a new feature to allow you to do this. I think that's what ended up happening.
Right.
Yeah. You know all about that, don't you?
Yeah. All right. Well, I mean,
I think that's a good place to wrap this up.
I come away from this, like, I'm glad that I learned something. I don't see, like, it's hard for me to visualize a place where I would actually use this.
Form data.
Where I wouldn't.
Form validation. what do you mean?
Yeah,
It's right here.
Right, but like, as we talked about, right, there are other ways you could approach this problem.
Yeah, that's true.
Admittedly, a more object-oriented fashion, but you also came up with some potential solutions yourself.
Yeah, I'm not actually sure about the value of phantom data myself, honestly. Like after reading through all this stuff and going through these examples, I guess, like, yeah, it's kind of nice that you can get this, like, I guess, type safety for free because there's no additional memory requirements here. But yeah, I'm not really sure. Like, I can't think of a lot of use cases for this, but I think I will at least try and make an effort to try and recognize more scenarios where I might want to try this and just kind of see, like, what are the benefits, what are the downsides.
Yeah, try it out. Why not? If you come across such a scenario, let me know. I'd be curious to.
Yeah, this actually has some pretty big problems in Rust, because if you have like a list of things like I described earlier with like dynamic dispatch versus static dispatch, that doesn't really work so well. In that case, you really do want to have sort of like a trait object or like a, I guess, like a class interface. So yeah, there are definitely downsides to this approach as well. But I think this is a good place to wrap this up.
Yeah,
thank you all for watching.
Yes, thank you all for watching. Put in the comments why we should use phantom types, because I still don't really know why.
Yeah, I don't really understand either. So yeah, leave a comment and let us know what you think.